Great. So hello everyone. My name is Bostjan Melinc, and I'm slowly wrapping up my PhD studies at the University of Ljubljana Faculty of Mathematics and Physics under the supervision of Ziga Zaplotnik. The main focus of my research is unifying background error covariance modeling for mid-latitude and tropical atmospheric data assimilation. And today I'm going to show you some of the main results of this PhD, which I obtained in collaboration with my colleagues from our atmospheric science group. As I said, our main focus is background error covariance modeling for relational data assimilation, where, for example, in 3dvar, we want to minimize this cost function j, which has two terms. The first one is the background term, and the second one is the observation term. And the background error covariances enter this cost function via the background error covariance matrix, or as I'm going to refer to it, the B matrix. The main challenge when employing this B matrix operationally comes from its size. Ideally, in global atmospheric models, the state vector of the atmosphere would contain up to 10 to the power of 10 elements, and B matrix should contain all the error covariances of all these elements, which would make B prohibitively large. And that's why operationally, they rather perform variational data assimilation in a control space, which is defined by some analytical transformations utilizing manually defined physical balances. So the idea is that the background error may be transformed to uncorrelated physical variables under the assumption that the errors in geostrophically balanced parameters are decoupled from those in the unbalanced parameters. And this then makes B matrix effectively block diagonal. Now, this idea of having either geostrophically balanced or unbalanced parameters is theoretically well based in mid-latitudes, but in the tropics we have a weaker Coriolis force, and therefore there are also other balances which are not adequately represented using these analytical transformations. And while it has been proposed in the past to tackle this limitation using normal modes as basic functions for the representation of B, this idea has never been tested operationally. But now we have a novel idea to tackle this limitation, which is to try to use universal neural network discrete transformations by an autoencoder, which can capture both mid-latitudinal and equatorial balances at once and perform variational cost function minimization in the latent space of that autoencoder. Now, what is an autoencoder? It is a neural network with a straightforward goal, which is to reconstruct its inputs. In our case, for the majority of experiments that I'm about to show you, we have an autoencoder which takes 20 global atmospheric input fields as its input. So these fields are geopotential height, zonal wind, meridional wind, and temperature at various levels. And then there's also mean sea level pressure and total column water vapor. And we train our autoencoder on error 5 reanalysis dataset. I won't go into the technical details of this autoencoder. The main thing is that the input enters an encoder, and the output from the encoder is the latent vector, which is labeled with Z. And then this latent vector enters the decoder, and the output is again the reconstructed 20 global atmospheric fields. The main structural property that I have to mention is the decompression that happens during the transition of those atmospheric fields through the autoencoder. So initially, these 20 atmospheric fields have more than 1 million features altogether, while latent vector only has an order of 10,000 features. So that's 2 orders of magnitude less. And we believe that if an autoencoder wants to learn how to successfully reconstruct its input, despite this severe compression, it has to learn the most important underlying physical balances behind the atmospheric states. So we can view this encoding and decoding as a neural network version of the control variable transform. And then we can rewrite the conventional 3dvar cost function in a way that it's now been minimized in the latent space of an autoencoder. Where this time in the background term, the state of the atmosphere, the background, and the background error covariance matrix are all defined in the latent space. While in the observations term, we only have one small change, where now the observation operator operates on the decoded state of the atmosphere from the latent space. Because when you decode the latent vector, you propagate it to the grid point space, and this allows us to keep on using conventional observation operator. And as in 3D var, also in latent space 3D var, we want to minimize this cost function jz. And the latent vector, which gives the minimum of jz, is latent space analysis, and we can propagate it to the grid point space by feeding it to the decoder. Now, I'll say a few words on how we tackle background error covariance modeling in this framework. The first option we tried was to employ a climatological B matrix in the latent space. In climatological B matrices, you need to compute a background error with a certain forecasting model and average this error over multiple time instances. And what we have is, in our case, the latent space background was an encoded 24-hour neural network forecast initialized by RFI3 analysis. For this, we had to train another neural network, and I'm not going for forecasting, and I'm not going into details here either. The point is we have a forecasting model of a decent quality, and we encode this forecast to get our latent space background. And the corresponding ground truth, which we use to finally get to compute the background error itself. So the ground truth is simply the encoded RFI3 analysis for chosen temporal instance. And then we average out this outer product over 5 years of data, and what we get is a B matrix, which is quasi-diagonal, which is great, because this allows us to only use its diagonal for inverse computation, which vastly speeds up the entire process. And let's have a look at some results that we get with this B matrix. So I'm going to show you 2 single observation experiments. First one in latitudes, where we observe 500 hectopascal geopotential height above Ljubljana. So the observation location is denoted by this yellow star. And this observation has a positive departure. And also the analysis increment of Z500 is positive, and it's surrounded by an anticyclonic wind increment, which both together indicate that geostrophic balance is preserved during the assimilation process. T500 increment coincides with Z500 increment, and it's nearly isotropic, but the same is not also true for example, 2-meter temperature increment, which is mainly confined to land. Now, why does this happen? This happens because typically the background variance of 2-meter temperature is much higher over land than it is over the sea. And we also see that the mean sea level pressure increment peaks eastward of the observation location, and its shape is deformed due to orography. So we also have some local features in our increments. We also checked that thermal wind balance is preserved during the assimilation, and therefore we can say that also the hydrostatic balance is preserved. And probably the most surprising thing is that our increments are already flow dependent when we are using this static climatology-based B matrix. This is because the B matrix itself is static in the latent space, but in our framework we also have this nonlinear decoder, which adds this flow dependency. So what we see in the figures is the arrows which correspond to the background flow, and you can clearly see how the shape of the increment is deformed due to this flow. And the final thing is that we can initialize the forecast by both the analysis and the background and have a look at their differences. And what we get is an eastward propagation of this initial Z500 increment and anticyclonic vorticity, while total column water vapor, mean sea level pressure, and 2-meter temperature increments altogether indicate that we have an emerging cold front here to the east of the Black Sea. So all in all, we can say that in mid-latitudes, we have analysis increments and the resulting forecasts, which are physically plausible. And now another example in the tropics, where this time we observe, we have a total column water vapor observation with positive departure. in a nearly saturated area in Central Atlantic. Our goal here is to induce saturation, and the theory in case of saturation says that eventually this will lead to lower tropospheric convergence and upper tropospheric divergence, and that's exactly what we see here. So we have analysis increments. Our analysis increment has lower tropospheric convergence, upper tropospheric divergence, and a continuous transition between them. The total column water vapor increment is elongated in zonal direction due to the typical lower tropospheric zonal winds in this region. And we even have a negative 2-meter temperature increment, which we believe corresponds to precipitation. And once again, we can try to initiate the forecast by both the analysis and the background and have a look at their differences. And this time, the total column water vapor increment is advected by the low tropospheric wind until it hits the coast of Brazil, while the 900 hectopascal wind increments indicate that we have an emerging eastward propagating Kelvin wave. So all in all, also in the tropics, we have analysis increments and the resulting forecasts, which make sense. Of course, we need not stop with the climatological B and can also test this framework using an operational ensemble of backgrounds. We are aware that these operational ensembles have a much lower dispersivity compared to the climatological variance on which the autoencoder was trained, and that neural networks tend to lose small-scale details, which is why we also have notable loss in variance in some variables after autoencoding, for example, as it's shown here for 500 hectopascal temperature. But we decided to proceed and model this EDA-based B in the Latin space as it's done for the operational ensembles. And what we get is, again, a quasi-diagonal B matrix, where this time the quasi-diagonality is not as well presented as it was for the climatological B. But given that the off-diagonal elements have similar magnitudes, we speculate that they only resemble sampling noise. And that's why we decided to once again continue with this radical approach to only use the diagonal for the inverse computation. And what we get if we repeat the same experiment in mid-latitudes, but this time with the operational ensembles with either the EDA-based B or climatological B, we see that the increments have quite similar patterns, and they only mainly differ in magnitude, but the latter is, of course, expected. The physical balances seem to be similarly preserved, and we get similar flow-dependent features, but we don't really have any substantial benefits from transitioning to the EDA-B. But hopefully in the future, with a more sophisticated autoencoder, which would resolve a larger fraction of ensemble variance, this may change. So to sum up this first part of my presentation, we propose a neural network-based method for background terror covariance estimation for variational lat assimilation of atmospheric observations in a reduced dimension Latin space discovered by an autoencoder. And we define a 3D cost function in this space, and the resulting B matrix is quasi-diagonal in both climatological and EDA-based setups, and it provides a unified representation of both tropical and exotropical covariances, which was our main research goal. The analysis increments are already flow dependent in case of static B due to the decoder's nonlinearity, but for the EDA-based B, for now, does not present any added value compared to the static B, probably due to severe variance loss in some variables. But hopefully this will change when we move towards more sophisticated autoencoders, and this is then a logical outlook for us. We are, of course, moving towards using more complex autoencoders now. If you found this presentation interesting, you can have a look at our paper that was published in James this January. And I'm going to spend the final 3 minutes of this presentation by discussing our current follow-up research, where our idea is that given that this framework showed promising results for unifying mid-latitude and tropical atmospheric covariance representation, maybe we can also use it for further unification of covariance representation. So what am I pointing at? In, for example, the IFS, the distinct Earth system model components are assimilated separately, while in our case, with a more sophisticated autoencoder, which would include multiple atmospheric, ocean, and land components, we would hopefully also capture these covariances, and this would allow us to perform strongly coupled data assimilation. And that's why we developed a new autoencoder. Again, not going into details. The point is, here we have even more atmospheric variables, more levels, and even some other Earth system model components, including 2-meter temperature and sea ice concentration. Now, why do I mention these two? Because in this slide here, we have an experiment where we observe 2-meter temperature with negative departure in the Northern Pacific. So the observation location is indicated by this tiny yellow dot here. And we perform this, we assimilate this observation in two different weather scenarios. So in the one hand, on the top, we have the background with the maximum sea ice concentration for the Northern Hemisphere, while in the bottom, we have the minimum yearly sea ice concentration in warm conditions. And in the top, when we assimilate this negative 2-meter temperature departure, what we get is a positive sea ice concentration increment along the sea ice, this initial background sea ice concentration boundary. And the 2-meter temperature increment is also affected by this boundary. While on the other hand, when we observe the same type of observation, but in warmer conditions, we don't have any sea ice concentration increment, and 2-meter temperature increment is nearly isotropic. So this indicates that we see this strongly nonlinear coupled response between sea ice concentration increment and between sea ice concentration and 2-meter temperature. And this really indicates that this method does indeed have also potential for fully coupled ocean atmosphere DA, and we will see in the future whether this may actually become plausible also for the operational work. So with this rather strong claim, I end my presentation, and I thank you for and thank you for listening, and I'm happy to take questions.
Awesome, thank you for your talk. That was a really nice talk. Thanks. We have about 2 minutes, so perfectly timed. So we do have a question from Mihai, I think. Hi, Bostjan, very nice talk. Interesting to see that the climatological covariance matrix comes out almost diagonal. Do you know why that would be the case? As far as I understand, you do not explicitly enforce sparsity for BZ. Thanks.
So we speculate. So, of course, when it comes to machine learning, it's a lot of speculation going on. We speculate that this comes from this severe compression, right? Because here, as I said, the autoencoder has this severely compressed input to get to the latent space and then back to the output. And to successfully reconstruct the state of the atmosphere, despite the severe compression, the latent space needs to be as expressive as possible. And that's why we believe that for the latent vector the latent space to become as expressive as possible, its elements become decorrelated, and that's what eventually also leads to this quasi-diagonal B matrix.
Awesome, thank you. So yeah, there's no more questions. That's it. Thank you for your talk.